We now discuss the solution of a problem from the section Real Analysis. And the question is related to the functions of several variables. And this is the second question in the same question paper. And this question has appeared in the CSIR National Eligibility Test held on 16th September 2022. And it is from part B. It is a multiple choice question and it carries 3 marks. The given question is, consider the function f from r square to r defined by f of x comma y is equal to x to the power of 1 by 3 into y to the power of 1 by 3 where xy belongs to r. Now, which of the following statements are true? Are true. So there can be more than one answer. So we are given 4 options. Option 1, the directional derivative of f exists at 0, 0 in some direction. Option 2, the partial derivative f suffix x does not exist at 0, 0. Option 3, f is continuous at 0, 0. Option 4, f is not differentiable at 0, 0. And we are given a function f from r square to r defined by f of x comma y is equal to x to the power of 1 by 3 multiplied by y to the power of 1 by 3 where x, y belongs to the set of real numbers. We have to discuss which of the following 4 statements are true. We now discuss the solution of the problem in detail. We take up the options one after the other and discuss the validity of those options. Now we take option 2. The partial derivative f suffix x does not exist at 0, 0. So let us see. So the partial derivative of f with respect to x at 0, 0 is equal to limit h tends to 0 f of 0 plus h, 0 minus f of 0, 0 whole by h. That is equal to limit h tends to 0 f of h0 minus f00 is 0. So substitute here f00 is 0 by h. Now f of h comma 0 is h to the power of 1/3 into 0 to the power of 1/3 is 0. So this is limit h tends to 0, 0 by h and that is equal to 0. So this tells us that the partial derivative of f with respect to x at 0, 0 exists and its value is 0, 0. That is f suffix x at 0, 0 is 0. And we require the partial derivative of f with respect to y at 0, 0 for the discussion of the differentiability of the function at the origin in the next option, in a subsequent option. So therefore, in option 2 it is given the partial derivative f suffix x does not exist, but it exists. Therefore, the option 2 is not true. We go to f suffix y at 0, 0 is equal to limit k tends to 0 f of 0, 0 plus k minus f of 0, 0 by k. So that is equal to limit k tends to 0 f of 0, k and by k where f of 0, 0 is 0. And that is equal to limit k tends to 0, 0 by k and that is 0. Thus the partial derivative fy exists at 0, 0 and fy at 0, 0 is equal to 0. We move on to the next option. So we have already calculated the partial derivative with respect to x and with respect to y at 0, 0 and each is equal to 0. Now let's take up the validity of the option 1. the directional derivative of f exists at 0, 0 in some direction, So if we can show that the directional derivative of f exists in some direction, then this option 1 will be true. Let us recall the definition of the directional derivative of f of x comma y at the point a comma b in the direction of the ordered pair u1 comma u2. E is given by, it is denoted by capital D of f of a comma b with suffix u1 comma u2, and this is to be read as the directional derivative of f at a comma b in the direction of u1 comma u2. And this is defined as limit t tends to 0 f of a plus t times u1 comma b plus t times u2 bracket close minus f of a comma b by t. If this limit exists, then the directional derivative in this direction exists. And suppose we take u1 comma u2 as 1 comma 0, that means along the x-axis. So the directional derivative of f of a comma b in the direction of 1 comma 0 is given by in the above definition. Simply substitute u1 is equal to 1, u2 is equal to 0, then you will get limit t tends to 0 f of a plus t comma b minus f of a comma b by t, and this is precisely the partial derivative of f with respect to x at a comma b. And it may be remarked that the directional derivative of f of a comma b in the direction of 0 comma 1, that is along y-axis, is precisely the partial derivative of f with respect to y at a comma b. Now let's get into our question. So now the directional derivative of f of x comma y at 0 comma 0 in the direction of 1 comma 0 is precisely fx. We have seen here. So that will be fx at 0 comma 0, and that is 0, and it exists. In some direction, in the direction of 1 comma 0 along x-axis, it exists. Therefore, our option 1 is true. That is, the directional derivative of f exists at 0 comma 0 in the direction of 1 comma 0, that is along the x-axis. Therefore, the option 1 is true. Agreed. Let's get into the next option. Option 3, f is continuous at 0 comma 0. So we take f of x comma y and f of 0 comma 0, take the modulus, and whether this can be made arbitrarily small, and whenever the condition, that is under the square root of x square plus y square, tends to 0 comma 0. So mod of f of x comma y minus f of 0 comma 0 is equal to mod of x to the power of 1/3 into y to the power of 1/3, because f of 0 comma 0 is 0. And modulus of the product is equal to product of their moduli, mod x to the power of 1 by 3 multiplied by mod y to the power of 1 by 3. Now, you see mod x is less than or equal to under the square root of x square plus y square. Mod y is less than or equal to under the square root of x square plus y square. So, this is less than or equal to, for mod x to the power of 1/3, this is under the square root of x square plus y square to the power of 1/3. Similarly, for the mod y to the power of 1/3. So this is equal to under the square root of x square plus y square to the power of 1 by 3 plus 1 by 3, that is 2 by 3. That can be made less than epsilon whenever under the square root of x square plus y square is less than delta. Delta is epsilon to the power of 3 by 2. 3 by 2. Thus, for any given epsilon greater than 0, there exists a delta, that is epsilon to the power of 3 by 2 greater than 0, such that modulus of f of x comma y minus f of 0 comma 0 is less than epsilon whenever under the square root of x square plus y square is less than delta. This means the limit exists. Limit x comma y tending to 0 comma 0 of f of x comma y is precisely f of 0 comma 0, and this is precisely the definition of the continuity of the function f at the origin. So therefore, f is continuous at 0, comma 0. Therefore, the option 3 is true. Right. We move to the last option, that is option 4. Option 4, f is not differentiable at 0, comma 0. And for this, we need the partial derivatives of f with respect to x and with respect to y at 0, comma 0, and both exist and each is equal to 0. Agreed. Now let's recall the definition. F of x comma y is differentiable at a comma b. It is in fact if and only if limit h comma k tends to 0, comma 0 of f of a plus h comma b plus k minus f of a comma b minus h times f, the partial derivative of f with respect to x at a comma b minus k times the partial derivative of f with respect to y at a comma b. The first two terms is the variation in delta f, and this is minus, this is df, this is the total derivative. By under the square root of h square plus k square must be equal to 0. This limit not only exists and it should be equal to 0. Right. So let's see. Now limit h comma k tends to 0, comma 0 of f of 0 plus k, comma 0 plus k, 0 plus k, b is also 0, minus f of 0, comma 0, minus h fx at 0, comma 0, minus k fy at 0, comma 0, by under the square root of h square plus k square. Fx at 0, comma 0 is 0, fy at 0, comma 0 is 0, f of 0, comma 0 is 0, and that will be equal to limit h comma k tends to 0, comma 0 is equal to f of h comma k by under the square root of h square plus k square. And f of h comma k is h to the power of 1/3 into k to the power of 1/3. Now let us take the limit along a particular path. That is, let h comma k tends to 0, comma 0 along the path k is equal to mh square. And if you substitute here, that will be h to the power of 1/3 into k is mh square, that is m to the power of 1/3 into h to the power of 2/3 by under the square root of h square plus k square is m square h to the power of 4, and everything is turned out to be in terms of h. Therefore limit h tends to 0. And if you see here, h to the power of 1/3 and h to the power of 2/3 in the numerator will be h into multiplied by m to the power of 1/3 by, in the denominator, h if you take out common, say h square common under the square root, it will come out as h into under the square root of 1 plus m square h square. As h tends to 0, this will be m to the power of 1/3. So the limit exists, but it varies from path to path. But the limit, whenever it exists, it should be unique. Therefore the limit does not exist. Thus the limit does not exist since it is not unique, as it depends on the path, and path means it depends on m and varies path to path. So thus the limit does not exist. So f is, therefore this is not 0. This does not exist. First of all, it does not exist. There is no question of not equal to 0. It does not exist. So therefore f is not differentiable. And I told you this definition is if and only if, not only just if and only if. So this implies f is not differentiable at 0, comma 0. Therefore the statement that is given in option 4 is true. Thus the option 4 is true. Right. Summarizing all the options. So the answer to this question is options 1, 3 and 4. In option 2 it was not true. So that is the detailed discussion of the solution of the problem from the section real analysis, and it is the second question that is appearing in this question paper on functions of several variables. And I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.